Okay, so tonight I'm going to go into all the nitty-gritty of digital modes. Let me start here and share my slides. Um, this always takes about three hands to do this right. There we go. And okay, so can people see can everybody see the slide that says General Class License Course? Well, I guess,
Yep.
Don, it's up to you. Can you see it?
Yep. Yeah, I can see it.
Okay, now I have to fast forward here. So it's going to take a minute. I'm just going to go right through all this stuff that we covered last week. Okay. So last week I said there are a whole bunch of different digital modes and their names and acronyms are alphabet soup and uh, and they're all good for different things. They're optimized for different things. So tonight I'm going to go through some of the theory behind them and then go for a tour of some of the more common modes. So what do we mean by digital modes? We mean something is a digital mode if we encode text characters as digital bits, and and that's not quite the whole definition. I mean, we stretch that a little bit. I mean, we do radio teletype and PSK31 and FT8, which are all data. It's all computer stuff that you recognize. But some people like to say that Morse code, CW, is a digital mode, and that's kind of stretching the definition a lot. And then slow scan TV is sometimes considered a digital mode, although the regulations say that those signals have to be in the voice segment of each amateur band. So anyway, and then there are digital voice modes, D-Star, DMR, and so forth that you find on VHF. And there are a couple of experimental digital modes that you can find on HF, although not too many people use them. So, so the digital modes that are text-based, excuse me, or exchange character text are limited to the CW data segments of each HF band. And in that, it's near the top of the CW segment, or in other words, just below the start of the voice segment. So the example here is there's a table in the book. The example here is that digital modes are found above 14.070 megahertz, 14070 kilohertz, and by gentleman's agreement or by general agreement, sort of, each digital mode has its own narrow set of frequencies where you can usually find it. Uh, the exception is when there's a radio teletype contest. You can find radio teletype signals all over the lower part of the band. So the data rates and the bandwidths are specified by the FCC. There's a rule that says that some digital codes protocols are specified in FCC regulations, but radio hams can use others as long as the specification or description is public. In other words, if it's published somewhere on GitHub or in a journal article or in an international standard, hams can use that. So what we can't do is we can't use encryption. Transmissions have to be in the clear. The original digital mode was radio teletype. And what happened was in the 1950s, radio hams started getting used teletype machines. and they used analog modems to translate between tones, and the electrical signal is used to communicate with teletype machines. Of course, nowadays you don't have that big mechanical hulk sitting in the corner of your shack. Instead, digital modes take place pretty much on computer screens and through audio cards. So digital modes have gone analog analog modems to digital modems, more or less. PSK31 is a common mode that's used for conversation. It's a text mode. It's fast enough that it is about as fast as normal typing speed, and it's also very narrow bandwidth, uh, which makes it nice for sharing on the ham radio bands. Pactor is a packet data packet mode, and I'm going to go into details of all of these. But Pactor is something that stands for packet teletype over radio, which is sort of a historical name that dates back to early in the internet years, because packet radio has a lot in common with the digital protocols that we use over the internet. WinMore is called Windows messaging over radio, and it's another signaling mode that's related to packet radio, and it is used very often for email. For instance, if you're sailing a sailboat on the ocean, chances are you keep in touch with home by using amateur radio and WinMore. Now, how legal that is in terms of message passing is a different question, but that's the common thing. Packet radio is most common on the VHF and UHF bands because signals there are not subject to a lot of noise and fading. So I want to talk about how fast you can go, and the rules changed last year, at the beginning of last year. It used to be that the FCC specified a baud rate for each different band. In other words, how fast you communicate digitally. And what they did was, at the end of 2023, they said, well, we don't care how fast you go, but the signal has to fit within 2.8 kilohertz bandwidth. In other words, the same bandwidth as a voice signal. So you can go as fast as you like, as long as your signal is narrow enough to fit in that bandwidth on the HF bands, 160 through 10 meters. Now, there are exceptions. For 60 meters, which is channelized, the baud rate limit is 300 baud. For 2200 and 630 meters, which are both below the AM broadcast band, the limit is 300 baud, although that's kind of unrealistic because 2200 meters is narrower, is very narrow. It's not even wide enough to transmit a single voice signal. 6 and 2 meters are the same. The baud rate limits are 19.2. There are 19,200 baud, or 19.2 kilobaud, and 1.25 meters, in other words, 220 megahertz, and 70 centimeters, in other words, 440 megahertz. The speed limit is 56 kilobaud. Above that, there is no speed or bandwidth limit, and the FCC is considering rules changes to change these baud rate limits to bandwidth limits instead. But for now, the important part of this slide is that for most of the HF bands, your data mode signal is limited by the bandwidth and not how fast you're communicating. I want to talk. Oh, here we go. So this is a little bit out of order, I guess. The digital signal band plane. You can see that for most of these, for instance, 80 meters, 40 meters, and so forth, digital mode signals are in the segment of the band that is specified for CW and data, but near the top of that segment. So, for instance, uh, on 80 meters, 3600 kilohertz is the start of the voice allocation, and the same at 7125 kilohertz. That's the start of the voice allocation on 40 meters, and so forth. And you can see, however, on 60 meters that you because 60 meters is channelized, you have to use, pardon me, you have to use the center frequencies of the five allocated channels, but you can use those frequencies on any mode. So it's a little bit screwy, but 60 meters is kind of the exception, in that it's shared with the military, and the FCC specifies frequencies that you must use rather than being able to tune around anywhere within frequency range. So I'm not gonna go into these any further, but you might see questions on the test that refer to these frequency segments. So let me give you some definitions here. Uh, that'll make sense for the rest of the slides. An air link is basically the frequency part of the communication link. So it involves radio transmitter and receiver, and the radio signals that are passed between them. A bit is just a binary digit. It's a zero or a one, and it represents a one bit of information. So the bit rate is the number of digital bits per second sent from one system to another. The baud rate is the number of symbols per second that are sent from one system to another, and I will talk about the difference on the next slide. The duty cycle is the ratio of time that a transmitter is on over the total time elapsed, which is the on time plus the off time, or transmit time plus receive time. And you can look at that two ways. You can look at that in terms of segments of several seconds when you're transmitting and then receiving, or you can look at that in terms of, for instance, when you're doing CW, you have a duty cycle that consists of dits and dahs that are on, that where the transmitter is on, but in between those individual signal elements, the transmitter is off. So the duty cycle is for CW is generally, when you're in a QSO, is less than 50%. Most digital protocols, when you're transmitting, the duty cycle is 100%. But given that you're having a back and forth conversation, when you look at it more longer term, like minute by minute, again, you're looking at something like 50% duty cycle. Protocol protocol is how data is encoded, or it controls the it can it's a set of rules that controls how data is exchanged between systems. But a mode is a combination of a protocol with a modulation method. In other words, how do the bits get onto the radio signal, and how are they demodulated from the radio signal? Now let me talk. Oh, now digital voice modes are treated as voice signals by the FCC, even though they have digital encoding. So, for instance, this list at the bottom, which are all digital voice that you typically find on VHF, are digital in terms of being transmitted as digital bits, but they're considered by the FCC to be voice signals because the end result is replicating your voice, or replicating the voice of the person doing the transmitting. So that's where the definition gets a little bit squiffy of what's digital. So let's talk about bits versus bauds. A baud is one symbol where you make a change in the signal modulation. For instance, switching from one audio frequency to another. Um, and a symbol can represent one bit, such, for instance, in frequency shift keying or phase shift keying, or it can represent multiple bits for instance, FT8 uses 8 different tones, and it can encode 3 bits in each baud because of that. Or some modes have multiple audio carriers. In other words, you're transmitting more than one tone at a time. You're transmitting multiple tones at the same time within your audio bandwidth. So um, if you think about it, if you think about it, FT8, because it uses 8 tones, one of 8 tones for each symbol, it can represent 3 bits. Or in other words, it can represent 8 different values, uh, and and eight eight is the number of values that 3 binary bits can represent. Um, if you stretch that out, the most common thing that we think of digital bits is in terms of bytes of 8 bits that can represent 256 values. And this will be important when I talk about radio teletype. So frequency shift keying is when you use 2 different tones to transmit. So you have a positive. So you're receiving a tone at all times when somebody is transmitting, and you use 2 different tones uh, for frequency shift keying using for radio teletype. They're called mark and space, which they're called mark and space, which is uh, um, represents mark represents 1, space represents 0. Good evening, Carrie. Hi there. You're still muted. We were a few slides in.
Yeah, sorry about that. Something came up.
No, that's okay. I've gone through some basic definitions and gone through some basic definitions which are all in your manual, and I'm talking about individual modes now. Just to recap, last week I said there's a whole alphabet soup of modes, digital modes. They all have different strengths and weaknesses. And this week I'm going through a tour of some of the more common modes. So anyway, frequency shift keying, your bits are encoded a 1 or a 0 is one of 2 different tones. Mark represents 1, space represents 0, and that goes back to the days of radio teletype. So in direct FSK, there are 2 different ways you can do this. One is you can frequency modulate your transmitter directly, so that the digital signal will directly modulate the VFO, which controls the frequency of your transmitter. So you have a carrier that's on one of 2 frequencies. Or you can do audio frequency shift keying, which is much more common these days, where on the HF bands, what you're doing is basically you have one of 2 audio tones, and that modulates a single sideband signal. So in essence, you have one of 2 frequencies, and at a time within the bandwidth of that SSB signal, and that's all you have is one of 2 tones, and so the rest, so there's nothing else there. Um, you can also have multiple FSK signals where you use I'm going to get a little bit wonky here and say you can use more than one audio carrier, which is to say you can use two different sets of tones, and each tone has a different mark and space frequency or a different frequency representing one and zero. So when you have multiple audio carriers, you can send multiple bits with per baud or multiple bits per symbol. So phase shift keying, the important thing to understand about phase shift keying is if you think about phase, um, if you have two sine waves and they're in phase, they look exactly the same. If they're out of phase, one is shifted in time. And what to know about phase shift keying is uh, the way it's used for PSK 31 is that invert the invert the you invert the phase of one of the tone waveforms. In other words, if you think of a sine wave, it goes positive, it goes from 0 to +1, back to 0 to -1, back to 0, and that's a complete cycle. Well, what you do in phase shift keying is that you flip the phase so that you're basically skipping one half of a cycle, and so you're moving the signal by 180 degrees in phase. Um, if that's not real clear, then we can talk about that probably next week. Rapid changes, what you can hear is PSK sounds kind of raspy or kind of ghostly because it's basically one tone, but the phase shifts introduce a buzz on that. And it sounds a little bit like a phone modem, but not too much. I mean, that for those of us who are old enough, it doesn't sound super like a phone modem. Anyway, you should be able to recognize that because radio teletype is two tones that go back and forth, so they sort of flitter or flutter, and a PSK signal is more buzzy. So let's do a few questions here. So there's only two of you, so speak up. What segment of the 20-meter band are most digital mode operations commonly found? A, near the slow scan TV frequency of 14,230, or B, at the top of the single sideband phone segment near 14,325. And remember, 20 meters goes up to 14,350 kilohertz. In the middle of the CW segment near 14,100, or D between 14,070 and 14,100. This should be an easy one.
No.
Anyone? I'm hearing silence. Okay. You weren't here for that, I don't think, Carrie. So I'll
But
give
is it
away
the
the
three
answer.
hertz separation or something? With everything
No, no, no,
being
no, no,
equal?
no. This is where in each amateur radio band you
Oh, the
find digital mode
digital.
signals.
Oh God,
Yeah.
I don't know.
Mhm. Yeah. So at the bottom of each band is a segment of each HF band except 60 meters is a segment set apart for CW and digital signals. And then the upper part of the band, which these days is most of the band, or at least the majority, is for voice signals. And so again, you find digital mode signals high up in the CW data segment and near the bottom of the voice segment. In other words, but it doesn't go into the voice segment. It's just like the top 50 kilohertz or the top 30 kilohertz of the CW data segment. And then within that, different different modes are commonly found in on frequencies that are a few kilohertz on frequencies that are a few kilohertz wide, and that's all by gentleman's agreement. How is direct binary FSK modulation generated? By keying an FM transmitter with a subaudible tone, by changing an oscillator's frequency directly with a control signal, by using a transceiver's computer data interface protocol to change frequency, or by reconfiguring the CW keying input to act as a tone generator. And you should be able to throw two of those out right away. So what do you think, Carrie, Don?
What was the answer to the previous one?
The previous one, well, the previous one was where in the band do you find digital signals? And this one is how do you generate direct binary FSK modulation? In other words, within the bandwidth of a single signal, how do you generate the frequency shift keying directly? And that has to do with how your rig works, how your transmitter works.
Probably B then, huh?
Yep, it's going to be, yeah, it's going to be B is B, yes. Now, mind you, that's less common these days because most people use their computer sound card to generate one of two tones that are then transmitted as single sideband, which gives you, if you think about it, which gives you frequency shift keying because the rest of the bandwidth of the rest of the voice bandwidth isn't used. How are the two separate frequencies of an FSK signal identified? Dot and dash, on and off, high and low, mark and space. This should be easy.
B. If it's
It
digital, right? It has to be
is
B.
D delta.
D. Oh,
Yeah,
D.
mark and space. This goes back to the early days of teletype. So that's something that has a history. Geez, that has a history. I was saying that Ham started using radio teletype in the 1950s, and so that is so that those terms come from 70 years ago. Which of the following provide digital voice modes? A, Whisper FSK 16 Easy Pal. B, FT8, FT4, FST4. C, WinLink Pactor 2 or 3. D, DMR, D-Star System Fusion. That should be an easy one too.
D.
That's right, it's Delta.
Delta.
And then the caveat here is that these three digital modes, DMR, D-Star, System Fusion, uh, and I think you could probably add P25 to that, are all found on VHF and UHF, but not on the high frequency bands. Okay, let's talk about some character-based modes here. So uh, you're, they're a way of transmitting characters or text, in other words, uh, to another station where they can be read by another operator. Now, CW, you read by ear. These other ways are you basically use your computer to encode and decode the signals. So the speeds are low, but it's convenient to use. You don't really need much extra equipment. As I mentioned last week, usually what you need is software running on your home computer, plus a sound card interface to the radio, which is usually a separate piece of equipment, like a signal link, for instance, or is built into the radio these days with newer transceivers. Um, and so sometimes you can refer to these as keyboard to keyboard modes or chat modes, and basically you're having a conversation with another ham over the air. And the the data stream is unstructured. In other words, it's just the characters of your conversation and nothing else. And this will get important when I talk about packet modes, which does include a lot of structure and some other things around the data you're trying to transmit. So radio teletype is the oldest form, and you can see the waveform here. Um, One character goes between this is voltage versus time. So voltage is the vertical axis, and time is the horizontal axis. And one character is represented by between the start bit, the start of the start bit, and the end of the stop bit. Start bit is always a space, there are 5 data bits and then 1 or 2 stop bits. And the idle the stop bits are always a mark. And when the connection is idle, you also transmit a mark. For instance, if you're typing away on your keyboard and you happen to pause to think of the next word, then your transmitter will be sending mark. Will be sending mark, which means there's no character in progress. And then as soon as the first space, the start bit is used to synchronize the receiver to the transmitter. So you know when you receive a start bit that there are going to be 5 data bits plus 1 or 2 stop bits. Now, you'll notice here, now this is Baudot code, which uh, the 5 bits, if you think about that in terms of binary numbers, 5 bits can represent 32 values. Well, you want to transmit letters, numbers, and punctuation. And if you think about letters and numbers, you're already at 36 characters. So how does radio teletype deal with that? Well, there are 2 special codes. So you get 30 characters, but you get 2 sets of 30 characters. In other words, if you send the letters code, then you know that everything following it will be the alphabet. If you send figures, then you know everything following that will be a number or a punctuation. And um, oh, okay. And then something to know about radio teletype is some teletypes are set up so that when you send a space character, it automatically drops from figures back into letters. And the reason for that is usually you're sending 1 or 2 numbers and then you send a space and you're back to more words. But not everybody does that, which means that sometimes you can see gobbledygook because the guy on the transmitting end may depend on you going back to letters on space, and the guy on the receiving end might not be set up to decode that way. Anyway, that's a quirk, and that's not gonna be on your exam, but that's one of the things that can go wrong when you're running radio teletype. The difference in frequency between the mark and space tones is called a shift of the signal. So that's the frequency shift and frequency shift keying. Um, Now, when you're talking, if you want a QSO if you want a QSO with a radio teletype station, then you have to enter him with the same speed and the same frequency shift. And also you got to be on the same sideband. If you're on the wrong sideband, again, you'll decode gobbledygook. PSK31 or phase shift keying is a little different. It was designed to be conversational, and it's called PSK31. PSK is phase shift keying. 31 is 31, or actually 31.5 baud, and it uses a sound card to generate the audio signals. That's not radio teletype. It uses a sound card to generate the audio signals that you modulate onto a single sideband signal. Sorry. So the symbol rate is actually 31.25 baud. Now, PSK31 uses binary phase shift keying, which is to say you can be one phase or the other phase, 180 degrees different. And so one transmitted symbol can only represent one digital bit. PSK31 is designed for chatting um, because it's equivalent to a typing speed of about 50 words per minute. Now, if you actually type a little bit faster and get ahead of it, software that you use will buffer will buffer the type ahead and it will just send it out at the same baud rate. And then, eventually you have to pause and the software will catch up to what will catch up in what it sends. It's also referred to as BPSK for binary phase shift keying, BPSK 31. There's also something called QPSK 31 or uh, quadrature phase shift keying that sends two audio tones. So there are now four possible phase shift combinations, two for each tone, which means you can send 2 bits per baud. Or in other words, go twice as fast for the same bandwidth. Now, QPSK has about the same bandwidth as binary PSK. Now, uh, PSK, well, like radio teletype and most digital modes, are sensitive to which sideband you're using. And most digital modes use upper sideband. PSK also uses a variable length character code called varicode, so that the most common letters are shorter than the less used characters. So, for instance, if you look at your computer keyboard, most of the letters in the home row are more commonly used, except for E and T. Well, I'm sorry. Uh, anyway, the most commonly the most commonly used characters like E, T, A, I, O, N are transmitted as a smaller number of bits than the less used letters like Q, X, Y, and Z. And um, also the capital letters and punctuation are transmitted using more bits than the most common letters. So um, PSK31 allows you to use normal capitalization. So if, for instance, if I'm talking with Bob, then if I say Bob, fine business, then I'll capitalize the B for Bob because that's the way his name is spelled. Um, and that's different from radio teletype. Radio teletype is basically all uppercase. It's not shouting, but it's just the limit of those limited alphabets that you have. PSK 31 has essentially all of the ASCII characters available. So it looks a lot more like normal text that you'd send in an email or when you're texting on your phone. So you don't need caps lock in PSK 31. So as I said, QPSK and PSK or binary PSK have about the same bandwidth. But QPSK 31 also provides some error detection because some of the extra bits that you send are used to detect errors in transmission. So let's do some practice questions. What is the most common frequency shift for radio teletype on the amateur HF bands? 85, 170, 425, or 850? Any guesses? Don, Carrie?
170? Did we see
Yeah,
that?
you're absolutely right. 170. Now, way back when teletype modems were analog, hams would use 850 hertz shift, and so as the technology's gotten better, the shift has gone down. But 170 is the most common one. Which of the following characteristics apply to QPSK 31? A, it's sideband sensitive. B, its encoding provides error correction. C, its bandwidth is approximately the same as BPSK31. Or D, all of these choices are correct.
D.
Yeah, Delta.
Right, it's delta, and I misspoke. There's a difference between error detection, where you can tell that where you can tell that you didn't receive something correctly, and error correction, where there are enough extra bits being sent that you can detect the most common errors. For instance, if one bit happens to get clobbered, or if there's fading briefly. So error correction, you send enough redundant bits that the decoding the data protocol can give you error correction. It can fix common errors. So you use a little extra data rate for that error correction. All right. Which of the following describes Baudot code? A 7-bit code with start, stop, and parity bits. B, a code using error detection and correction. C, a 5-bit code with start and stop bits. Or D, a code using cell call and listen.
C.
Yep,
Yeah.
C, Charlie. Is this, Don, is this stuff clear to you, or is it all still alphabet soup?
It's alphabet soup, you might as well say. But I missed you on the first couple because uh I wasn't on speaker. But yeah, it's pretty tough. It's all new to me.
Okay.
Yeah.
I'm going to say that this stuff is pretty arbitrary, so you should definitely read and be taking the practice tests for this, um, because this stuff does come up. Some of these are right out of the exam, and you will be asked several questions about data modes. So even though it all sounds kind of arbitrary right now, unless you get some experience with these modes, this is stuff that you really should work hard to memorize. And Carrie, you're doing a little bit better, and I think I think that as the evening goes on, you're going to get into familiar territory too.
Yeah,
Anyway,
this is
the answer.
pretty Greek to me.
Okay, well, the answer is Baudot code used for radio teletype is 5 bits, 5-bit code with start and stop bits. Which of the following statements is true about PSK31? A, uppercase letters are sent with more power. B, uppercase letters use longer varicode bit sequences and thus down transmission. C, error correction is used to ensure accurate message reception. Or D, higher power is needed as compared to radio teletype for similar error rates.
Probably D, huh? I'm just guessing.
I was going to say A.
Okay, so we have A and D, and I'm sorry, but the answer is B.
B.
I was talking about varicode where more common letters and lowercase are sent using shorter codes than uppercase letters and less common letters, excuse me. So
Yeah.
now, you slow down transmission, if you're typing away or if you're in the middle of a QSO, you're not going to notice it. But as far as how fast in terms of data rate it goes, yeah, when you send uppercase letters, the data rate is somewhat slower because the characters are sent using more bits. What type of code is used for sending characters in a PSK31 signal? Varicode, Viterbi, volumetric, or binary? I was just talking about this.
The varicode you were talking about.
Yep, it's
Yeah.
varicode.
Yeah. I
That's
agree.
right. So let's talk about packet-based modes. And this is, how are we doing for time? Okay. We'll probably take our break right after this section. Packet-based modes, uh, these are called structure modes because they're similar to internet or computer to computer network protocols. And as a matter of fact, they have their origins pretty much the same place as the early protocols used on the internet. So what you get here is additional information sent besides the, I'm sorry, additional data is sent besides the information that you're trying to communicate with the person at the other end. Um, Hams have adapted computer protocols to create packet radio, Pactor, Winmore, other communication systems. This stuff goes back, I think, to about the 1980s. In other words, it follows the rise of computer networking by just a few years. Um, and as a matter of fact, a lot of material you'll find about this, it was a really hot idea back in the 1980s and 90s, and maybe not so much now because you don't need special hardware anymore to do it. You can use your computer. So some of these things are just other modes that you can use with your computer. Some packet modes require, some packet modes like JT65 and FT8 require precisely defined uh, transmission periods. And I'm going to talk about these JT65, FT8, FT4, and some similar ones are also called weak signal modes. And they depend on very accurate timing to know more or less when to start listening for a transmission. And FT8, you have to keep your computer synchronized to within 1 second of UTC, Universal Time. And there are utilities that you can use to do that. And they talk to time servers on the internet, or some people have GPS receivers that they hook directly to their computers. But the idea is you can get very accurate timing that way, where your clock and a computer clock anywhere else in the world is listening to your signal are pretty nicely lined up. And the software you use for these modes, you can tolerate some variation up to 1 second, which is actually a lot more than most people use. Most people are accurate to within a couple tenths of a second. Anyway, packet basis. Let's go back to packet radio here. A packet refers to transmitting data inside of a structure called a frame. And the elements of the frame, I hope everybody can see that. The elements of a frame are, you have a header, the data segment, which is your payload, which is the data that you want the person at the other end to be able to receive, and then a trailer. The header contains synchronization and routing and control and status information. The trailer contains status and error detection data. And um, the idea is that the software that you use to transmit these signals adds the header and the trailer to the data segment. And also, if you have a lot of data, let's say you want to transmit a page from War and Peace, which is a couple thousand characters, the software will break it down into shorter packets that can be sent more reliably over the radio. And so all of this stuff is invisible to you as the end user, just the same as when you're receiving an email, or you're looking at a web page. You don't realize that this thing that says click here for cat video is actually transmitted as several much shorter packets, and not a whole several kilobytes at a time. Anyway, the packet refers to transmitting data within a structure, and the extra parts of the structure are for control and to ensure the quality of the packet, and for orderly flow of data between transmitter and receiver. So, okay, this is just what I went through here. Different packet protocols use different sets of information in the header and the trailer. Header usually starts with a synchronization pattern, so that the receiver, or actually the software that does the decoding, can adjust to the timing of the incoming signal. And then it contains control information, sometimes routing information, sometimes information about detection, error detection or correction. Um, and the control information usually includes information about how long the data segment is going to be, so that the software on the receiving end knows how many bytes of data to listen for before it starts listening for the trailer of the packet. So the data is usually ASCII characters. In some protocols it's compressed. It's compressed the same way that you would use, say, zip to compress your files. The idea is that ordinary text doesn't make very efficient use of bits. There are a lot of bits that are kind of redundant or not used. And so when you compress data and uncompress it at the other end, you can
Can you
send
tape it?
longer message in the same
Can you
amount of
tape it?
time. The trailer is used for error detection, sometimes error correction, uh, and most often includes something called a cyclic redundancy check, which is a fancy math way of mashing together all the bits in the data segment to get a signature, a data signature that's hard to duplicate by any other data pattern. So what the CRC, the cyclic redundancy check, can tell you is if you received everything correctly, or if there's some error, it falls down when there are a lot of errors in the received data packet. But when there are just a few, it's pretty good at telling you that everything is okay or it's not. And usually what happens when you detect errors, we'll get into this, but the receiving station sends a message back saying, try again. So we're going to get into automatic repeat and request, or ARQ systems, which automates this process. And if so the receiving station will receive a packet and it replies either as part of a data packet going in the reverse direction or as a short burst of data. It will reply with an acknowledgement or ACK, which says everything's okay, or a negative acknowledgement or NACK that says, "Oop, there's a problem here." And so usually the protocol is set up so that if there's an error on the receiving end, the transmitting end will send the same message again. And that way, with any luck, it gets through without errors. So the transmitting session is, if the receiving system is receiving packets with errors, transmitting system will resend the same packet until it receives a positive acknowledgement from the receiver, from the receiving station, or until it times out, until it's sent the same packet too many times. In which case, your connection between transmitter and receiver is kind of hosed. ARQ is used in a lot of packet radio modes like PACTOR, Packet Radio, WinMore, and automating the process means that the operator doesn't have to worry about it unless things go badly wrong and you can't get through it all. So the ARQ protocols were designed for wired network connections, and where where you have a pair of wires going from one station to another. Well, in the case of radio, the the uh, the retry mechanism only works between one transmitter and one receiver. So if you just turn on your radio and you're listening to a packet radio signal, if you get a packet with errors in it, you cannot request can't request you can't request a retry because you're not the person that the guy who's transmitting is talking to. Don, I'm not sure why I'm seeing your screen there. Anyway, what that means is you can't break into an ongoing contact. In a voice contact, yes, you can. But in a packet radio contact, it's basically one to one. So one station contacts another and they have a conversation, and it's just that one to one relationship until they're done, as opposed to a roundtable. Probably by now on repeater, you have gotten into a situation where there'll be two or three people or even more talking, and people will go round robin, or somebody will break in and ask a question or give a brief answer, and then you go back to the regular conversation. But for ARQ modes, for packet radio modes, you can't do that. So a station can advertise its presence. So there's a broadcast mode. So it can transmit and say, hey, is anybody out there, or is so-and-so out there? But other stations can interpret that without necessarily having to first establish the contact. So in other words, the station can advertise in order to begin a contact, and then it's one to one when the connection is established and you're in the middle of a contact. I know this wording uh, is a little bit confusing. There's also a monitor mode. So there's also a monitor mode provided in packet software so that you can explicitly listen to other conversations without transmitting, without taking part directly, without responding to the transmitting station. But you can listen in the same way you can listen in on voice or CW transmissions. So using the monitoring mode, you can determine if the frequency is busy, and that's actually a good thing, because you don't want to get in the middle of a conversation between two other stations. You don't want to break in, because that disrupts the connection that the two stations who were on the frequency already, that disrupts the connection they have. So this is another example of listen before you transmit. So the TOR, or teletype over radio systems, uh, some of them can compensate for transmission errors. Um, and uh, and those are used mostly on the UHF bands, and they're used for networking via radio, much the same way as there are wired communication networks, or much the same way as the internet that comes out of your wall socket, or over your cable system, is used for computer networking. Pardon me. So packet radio systems that are used mostly on UHF um, send short bursts, send short packets that include error detection and correction, and the operation is fairly automated. So the most common one is based on the X25 computer network protocol, which is a computer-to-computer standard. And it was popular in the 1970s and 1980s. And it's one of the oldest computer-to-computer protocols that exist. And it was around before it was adopted for radio communication. Uh, Packets are usually exchanged using VHF, FM, or UHF FM at 1200 or 9600 baud. And there's work going on now to increase data rates, but those are the most common for off-the-shelf equipment and off-the-shelf systems. It doesn't work well on HF because the data transmission can easily be disrupted by noise and fading. And if you remember from the first week when I played examples of different signals on HF, there was a lot of noise. So um, so anyway, packet radio is designed for higher data rates, and because of that, and because it's not resistant to noise and fading, it's used mostly on UHF where you have line of sight communication that's low noise. So the original protocols, Amtor and GTOR that come from way back are reliable, but they're slow. And there are improvements since then. PACTOR and WinMore um, are improvements that go faster and are more reliable. Um, so the idea is to do the same but better. PACTOR 1 uses frequency shift keying, uh, and the more recent versions use PSK, and apparently PACTOR 4 goes too fast, so it's not legal, or uses too much bandwidth, one or the other, so it's not legal yet in the US. Um, PACTOR and Vera modes can overcome some of the issues with HF. In fact, Vera is a proprietary mode that's used for HF communication. As I was saying, sailboats in international waters use Vera on ham radio for email because it's reliable on HF despite fading and noise. WinLink WinLink sits on top of these protocols to transfer email and digital files on the HF bands, and it's a gateway communication system. In other words, it's not a digital mode, but sits on top of a digital mode, excuse me, and turns it into something useful. The same way as when you send an email, there are internet protocols that actually send the characters and make sure they get to the right place. But what you see sitting at your computer is an email that's text and has a to and a from and a subject, because all the details are hidden. But your email program works on a higher layer of information sharing. It's the same way with WinLink. It sits on top uh, of some digital modes that are less structured. So it uses the internet to connect email servers with stations, with amateur radio stations around the world on HF, VHF, and UHF. Uh, WinLink stations don't connect directly with the internet, but rather messages are forwarded through gateway stations between the internet and WinLink stations that are active on RF. And so the idea of having a mailbox where your mail sits, or your messages sit for a little while before somebody picks them up is a good one here. But even without the internet, WinLink can act as a standalone mail system between stations, or can let stations communicate directly with each other. On HF, WinLink uses PACTOR and Vera. Vera, as I said, is a proprietary mode, and you remember that I said that the FCC rules say that a data mode has to be specified. The details have to be specified in public. With Vera, that's kind of iffy, but on the other hand, the FCC seems to look the other way on that.
Hey, you.
Um, Vera is one of the few modes where you cannot go somewhere on the internet and find a complete specification right down to the bit level. Let me talk about weak signal modes like FT8 and Whisper. WS stands for weak signal. The software you use to run it, WSJT-X, is the WS stands for weak signal. The idea is that you have these modes that are designed to work at low signal to noise ratios. What they do is, and with low power and narrow bandwidths, what they do is they use a lot of redundancy and they go slowly, so they have resistance to noise and fading. FT8 in particular has synchronization at three different places in each transmission, and it uses a lot of redundant bits for error correction. And there are articles you can read about the coding. The coding is really elaborate. And FT8 comes from work that a guy named Joe Taylor, who happens to be a Nobel Prize winner, did in communications with satellites that are traveling between planets. In other words, really weak signals and low data rates. And he's adapted that for the amateur bands. So the FT8 signal FT8 packets are 75-bit messages that are limited to call signs, grid locators, signal reports, and things like acknowledgments. Now, the thing about FT8 you have to know is that every conversation says the same thing. It follows a very rigid format with very few deviations allowed. And so, as I say, the coding is elaborate to get the most out of those 75 bits that you're allowed in each transmission. FT8 FT8, excuse me, usually occupies about 3 kilohertz. In other words, the width of one single sideband signal per band. FT4, which is the same protocol but twice as fast and more designed for contesting. Uh, also uses 3 kilohertz on each HF band. Um, let's see. Whisper is something that is designed for one-way transmissions. The idea is if you operate a Whisper node, every so often you will send out a data transmission, and then the idea is that other stations will listen for you, and you will listen for other stations, um, and then all these stations communicate to a central hub via the internet. So you can go on the internet and see where your signals are heard. So it's useful for determining where propagation exists from Michigan to other parts of the US, or from Michigan internationally, or for that matter, from anywhere in the world to anywhere else in the world. Um, and this is something that's actually quite popular for people to use to determine, well, what band should I be on, or who might be able to hear me. Now, the thing to know about FT8 and Whisper are FT8, most people use reduced power. If you use 100 watts for a single sideband or CW signal, which is really typical, you might use only 20 or 30 watts for FT8 because FT8 works at lower signal to noise ratios. So you don't need as strong a signal to get the same results. And Whisper is even lower power because it's very slow, and it's designed so that at the receiving end, the software can decode signals that are at very low levels compared to the noise. So here, what we do is, if you go to whispernet.org, you'll be able to see where various stations are being received. And Whisper can also be used. Whispers also used. There are ham radio balloons that are sent up. This is something that was sent up in, I think, 2016, and it went around the world several times at about 40 to 50,000 feet. And it was just a helium balloon with a few ounces of radio attached. And it transmitted these whisper beacon signals every so often. And I believe that the signals included telemetry that included the altitude and the outside temperature and probably the battery voltage. So I think this thing was aloft for more than a year, and you can see by the tracking that it went around the world several times. And since it drifted on the winds up in the stratosphere, you can see that it didn't take a very straight path going around. And at any given time, there are probably one or two dozen amateur balloons that are up in the stratosphere, and it's all quite legal. I think you have to notify the FAA that you're doing this, but otherwise it's perfectly fine. And these balloons are better than what you buy at the party store, but they're not as fancy as, say, weather balloons. Now, you may remember a few years back, the U.S. shot down a Chinese balloon after it had drifted over most of the U.S. And the pictures that we saw of a SR-71 flying past it showed that it had a lot of equipment attached, and it was taking pictures of whatever was beneath it. And it was a Chinese balloon. Well, so China has done that. It sent balloons for a more, excuse me, strategic purpose than a more strategic purpose than ham radio balloons. But then you may recall that a couple of weeks later there was an unidentified balloon over Alaska, and it got shot down over Canada, over the Yukon, and the remains were never found. And the reason for that is it was probably a ham radio balloon that was detected on radar, but it was just an innocent thing, but everybody was on a hair trigger because of the Chinese spy balloon that had come through. Anyway, that's a little bit of history that nobody wants to talk about because I think it's kind of embarrassing to the Air Force. All right, what time is it? Oh, it's 8:15. We're going to take a 10-minute break here, and please come back at 25 past the hour. I'm going to stop sharing here. Please come back at 25 past the hour, about 10 minutes, and I'm going to take a break here too. I'm going to start up again. Okay, so I'm going to share my screen here. Can people see the thing that says Amateur Wireless Networks?
Yep, look good.
Yeah, got it.
Can you see the thing that's just the one slide, or does it include
Just one.
just one? Okay, so you don't see a small one to the right.
Yeah.
I do. I see
Yeah.
I see a little slide and a big slide.
Yeah, we've always
Oh,
seen
okay.
that, Wes.
All right, let's see if I can get it to work properly then.
Yeah, your whole first half was that little one in the corner.
Oh, well, you're not supposed to see that.
Oh, that's the
I
teacher's
wasn't
crib?
looking.
Let's try this one.
Okay.
How's this one?
Hey,
Is that
Hey,
just the one slide?
it's
Yeah,
big
now
too.
it's just one big one.
Yeah, that's good. Okay.
I can read
Okay.
that without glasses.
So let's talk about shared bands and wireless networks. Um, some of the bands that are available for unlicensed use for wireless networking also are amateur radio bands. For instance, the 2 gigahertz Wi-Fi band more or less overlaps the 2 gigahertz ham radio band. So you can use the Same equipment, you can use the same frequencies as say say the router that's sitting in your house, but the difference is you can use them for pretty much the same purposes as unlicensed users, ordinary wireless networking users. But the thing is, you cannot encrypt signals. Now, most Wi-Fi, if you follow the security recommendations, you have a password on your home network, and you'll find passwords on networks, Wi-Fi networks elsewhere too. And part of that is so that your neighbor doesn't steal your internet, but part of that is for computer security, so some passerby can't pry into your private business. Well, the password is part of the encryption scheme, so that the packets that you send over the air are encrypted uh, when, when they're radio signals. Um, but to use that same equipment, as a radio ham, um, to be legal under amateur radio regulations, you got to turn the encryption off. And that's a long-standing FCC rule that you can't make secret transmissions using your amateur radio license. So it's something you got to watch out for. But that has not stopped radio hams from repurposing wireless networking equipment for their own purposes. So we use radio networks that have the same layout or topology as ordinary wireless networks and wired networks, like in an office building. Um, Mesh and star. Star means that there is a router or there's some master node at the center of everything, and communication radiates out to end nodes. Mesh networking means that messages are passed from node to node to node, and is not necessarily very organized. It's just whoever is there and on the air uh, becomes part of the network, and any node can pass messages as an intermediary between two other nodes. So mesh networking, the advantage there is if one node fails, if one station goes off the air, often uh, there are other paths that can route around it, maybe more indirectly, but the network is resilient. It can withstand failure. So this is where unlicensed bands overlap amateur bands. You can see 900 megahertz is used for industrial communications, and I think uh, some cell phone communications. 2.4 and 5 gigahertz are used for Wi-Fi, and there's a typo on this slide. I think that last entry under ISM goes to 5875 megahertz. And then the 3 gigahertz band is also used for, I believe that is an additional Wi-Fi band for newer versions of Wi-Fi. But it can also be used for other unlicensed uses, such as industrial controls. So in this case, the high-speed amateur wireless networking shares bands with other types of users. And so it's also subject to interference from other types of users, for instance, from home Wi-Fi. Um, the network we're talking about here, that's high speed and uses these gigahertz frequencies, uh, most commonly is a RADIN, or the Amateur Radio Emergency Data Network. it uses available router hardware with special software, and it's a mesh network, meaning that it can be set up pretty much anywhere, and it organizes itself. And if something fails, then the a node then messages can be routed around a failed node. And these are used for emergency communications and to support events, public service communications like communications during road races and foot races or parades or things like that. And get data communications, whereas, um, for instance, I think that a lot of our Hazel Park members have in the past used their HTs as part of a voice net for running something called the Oak Apple Run, which used to be run every year in Royal Oak, where there would be hundreds and hundreds of people doing short and 5 and 10K races through city streets. And radio hams were there to call medics if there was a problem, or and to give the net control, to give the people at the headquarters some idea of where the end of the race was. So we can do that with data now. So let's do some questions here. What is Vera? Is it a low signal to noise digital mode used for Earth-Moon-Earth communications? In other words, moon bounce. It's a digital protocol used with WinLink, a radio direction finding system, or a DX spotting system using a network of software-defined radios. Don?
I remember
Karen?
you said sailboats use it.
Let me unlink. I was going to say B.
Yeah, the answer is bravo, B. Yes, it's a digital program used with WinLink, and yeah, sailboat owners use it for email while they're on the high seas. Which of the following is good practice when choosing a transmitting frequency to answer a station calling CQ using FT8? A, always call on the station's frequency. B, call on any frequency in the waterfall except the station's frequency. C, find a clear frequency during the same time slot as the calling station. Or D, find a clear frequency during the alternate time slot to the calling station. And I'm sorry, I
We lost you.
Wes, you're frozen, I think.
Yeah, we're not here. Not here.
Yeah.
I'm sorry. I think things froze up at my end. Has anybody got an answer that they want to guess?
I was going to say A.
All right. The answer is actually D. The way FT8 works is stations take turns in alternate time slots. So somebody will call CQ in a slot that begins at 0 seconds, and stations will answer in the time slot that begins at 15 seconds past the minute, and then two stations will alternate in the 15-second slots, so that station transmits for most of 15 seconds, and then it listens for 15 seconds, and they alternate. And I'm sorry, we didn't cover that, but that's the way FT8 works. And what you want to do is you're transmitting in the other time slot to the guy you're trying to talk to. And so what you want to do is try and find a frequency within the 3 kilohertz or so bandwidth that FT8 occupies. Find a frequency that nobody else is transmitting on, so that the guy you want to talk to can actually hear you without interference. And I'll have a few more words to say about that when I talk about waterfalls. Which of the following is required when using FT8? A, a special hardware modem. B, computer time accurate to within about 1 second. C, a receiver attenuator set to a minus 12 dB, or D, a vertically polarized antenna.
Bravo.
Yeah, bravo.
Yeah, it's Bravo. Your computer time needs to be synchronized to time servers on the internet or to GPS within about 1 second, which, by the way, is very easy to do. How do you join a contact between two stations using the PACTOR protocol? A, send broadcast packets using your call sign while in monitor mode. B, transmit a steady carrier until the PACTOR protocol times out and disconnects. C, joining an existing contact is not possible. PACTOR connections are limited to two stations. Or D, send a NAC code.
C.
See, yeah,
D,
see,
yeah, it's kind of a trick question. Yeah, in PACTOR and other packet radio protocols, you can listen, but you can only participate with one other station. So if two people are talking to each other, you can't join that conversation. What is the primary purpose of an amateur radio emergency data network, mesh network? A, to provide FM repeater coverage in remote areas. Pardon me. B, to provide real-time propagation data by monitoring amateur radio transmissions worldwide. C, to provide high-speed data services during an emergency or community event. D, to provide DX spotting reports.
Probably C.
Yeah, it's Charlie. It's a high-speed network that used for emergencies or community events. Yeah. Um, Bravo, the answer Bravo was Whisper, if you recall. It's set up so you that stations transmit and then go on the internet to see where their transmissions were received. And then there are things called spotting networks where people some of them are somewhat automated. So if you send a CQ using CW or I think maybe radio teletype, some automated nodes will spot you and say that you were heard. But DX spotting is normally kind of a manual activity where the person operating a station will say a spot will type in a spot saying, "Oh, I heard such and such a station," and that's another way to tell where signals are propagating or who you might hear if you see spots if you see spots saying that stations near you heard a particular DX station. Anyway, which of the following describes WinLink? A, amateur radio wireless network to send and receive email on the internet. B, a form of packet radio. C, a wireless network capable of both VHF and HF band operation. Or D, all of the above.
All of the above.
That's right, it's D, all of the above. Uses radio and can forward messages between radio links and the internet. Delta. What is another name for a WinLink remote message server? A, a terminal node controller. B, a gateway. C, RJ45. Or D, a printer server.
B.
Yep, the answer is B, it's a gateway. Which of the following is a common location for FT8? A, anywhere in the voice portion of the band. B, anywhere in the CW portion of the band. C, 14074 to 14077. Or D, about 14110 to 14113.
Charlie.
Yeah, Charlie. That's right. And as a matter of fact, FT8 is on several of the bands is located about 70 kilohertz above the bottom edge of the band. Sorry, yeah, the answer is Charlie. Sorry about that. What type of modulation is used by FT8? Eight-tone frequency shift keying, vestigial sideband, compressed AM, or 8-bit direct sequence spread spectrum. Boy, see that 10 times fast.
Well, D is a cell phone. It's got to be A.
Yep.
Yep, it's A. It's 8-tone frequency shift keying. What is QPSK modulation? A, modulation using quasi-parallel to serial conversion to reduce bandwidth. B, modulation using quadrupole sideband keying. C, modulation using fast Fourier transforms to generate frequencies in the first, second, third, and fourth harmonics of the carrier frequency. Or D, modulation in which digital data is transmitted using 0, 90, 180, and 270-degree phase shift to represent pairs of bits.
Delta.
Yeah, I apologize. The answer is delta, and that means that the explanation I gave earlier is wrong. QPSK does not use two separate tones. It uses one separate tones, but four phase angles. Four phase angles separated by 90 degrees instead of two phase angles separated by 180 degrees. And which digital mode is used as a low power beacon for assessing HF propagation? A, whisper. B, MFSK16. C, PSK31. D, SSB-SC.
A. Like that
Yep,
balloon, right?
the answer is A. SSB-SC is the original name for single sideband. The full name is single sideband suppressed carrier. What part of a packet radio frame contains the routing and handling information? A, the directory. B, the preamble. C, the header. D, the trailer.
Header.
Yeah, C, the header. Now, just to confuse things, sometimes you'll hear the word preamble used to sometimes you hear the word preamble used to describe the synchronization part at the very beginning of a packet. And so the preamble is part of the header, but it's used for synchronizing the receiver to the transmitter. In an ARQ mode, what is meant by a NAC response to a transmitted packet? A, request retransmission. B, packet was received without error. C, receiving station connected and ready for transmissions. Or D, the entire file was received correctly.
Got to be A.
Grade A, NAC is negative acknowledgement. Which of the following narrowband signal modes can receive signals with very low signal-to-noise ratios? A, MSK144, B, FT8, C, AMTOR, D, MFSK32.
Wasn't it Amtor?
B.
Well, I think the answer is going to be B, but also MSK144 is a weak signal mode also. So this is a little bit of a trick question, but the answer they're looking for is FT8, and that's the one you're going to run into most commonly. What is true of mesh network microwave nodes? A, having more nodes increases signal strength. B, if one node fails, a packet may still reach its target station via alternate nodes. C, link between two nodes in the network may have different frequencies and bandwidths. D, more nodes reduce overall microwave out-of-band interference.
B.
B. Yeah, B for Bravo.
Yeah, B, bravo. It's got some redundancy against failure. How does forward error correction allow the receiver to correct data errors? A, by controlling transmitter output power. B, by using the varicode character set. C, by transmitting redundant information with the data. Or D, by using a parity bit with each character.
C. Charlie.
Yeah, it is C, Charlie. I have a feeling, Carrie, that we're on familiar territory for you.
No, I have a pretty good memory. I have not looked at this stuff. I just remember what you said.
Okay. Yeah, the answer is forward error correction Okay. The
I don't
reason
know
it's
if
called
I'll remember it, much longer, but my short-term memory is still good.
the reason it's called forward error correction is instead of fixing errors by retransmitting, in other words, a two-way system for error correction, uh, the 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 extra information needed to correct errors, to correct bit errors, is included in the packet going in one direction.
You said Charlie?
Yeah, it's Charlie. It's
Okay.
Charlie.
Okay.
Yeah, so you send extra bits, and that way you can detect common errors, 1, 2, 3 bits out of your packet received an error. There's enough redundancy that you can tell where something is in error and you can fix it. What does an FT8 signal report of +3 mean? This is also something we didn't cover in the slides, but you can sort of figure it out. The signal is 3 times the noise level of an equivalent SSB signal. B, the signal is S3 on the S meter. C, the signal to noise ratio is equivalent to +3 dB in a 2.5 kilohertz bandwidth. Or D, the signal is 3 dB over S9.
Hmm.
It's okay to
Didn't
guess
you
on this
talk
one.
about that last time? Maybe that it might be D?
Well, okay, the answer is C, Charlie. Um, Part of the FT8 exchange is you'll send a number that's a signal to noise ratio, and it's usually somewhere around zero. It can be positive or negative, and that is how strong is the signal that you're receiving from the distant station compared to the noise in an entire bandwidth of an SSB signal, which is, by the way, much wider. So the the FT8 signal from one station is about 50 hertz wide, but a single sideband signal is about 2.8 kilohertz wide. So because noise is dependent on bandwidth, um, that means that if you're listening with a wide receiver bandwidth, you'll hear a lot more noise compared to just what's the noise that's in that 50 hertz occupied by the FT8 signal. That's why you can see negative numbers. But that's actually part of the exchange between two stations. Is on the second or third message, you'll send a signal report to the other station, and that's why when you see signal reports, it's going to be a plus or minus number instead of an S meter reading when it's FT8. All right, so let's go into receiving and transmitting digital modes. Most will transmit digital modes on the upper sideband. That's just a convention, except for radio teletype. You use lower sideband. Now, you may remember that Marv a couple of weeks ago said that single sideband is on upper sideband above on 10 megahertz, on 14 megahertz and up, and it's on lower sideband on 7 megahertz and below. But digital signals don't follow that convention. Instead, digital modes, except for radio, are normally on upper sideband, and radio teletype, for historical reasons, uses lower sideband. So you have to configure your modem or more likely your software, your digital mode software, to the correct baud rate and the correct tone frequency, and your radio has to be listening on the proper sideband. And all these things have to be correct, even if you're hearing a strong signal. Otherwise, you'll see gibberish decoded, or else you won't receive the signal at all. Or rather, you won't decode the signal at all. Now here, want to talk again about bandwidth here. The bandwidth of a signal is proportional to the signal to the symbol rate. So the faster you are sending symbols, the more bandwidth you use. That's one reason why on HF where bandwidth is more limited than on VHF, the data rates are slower. And so yeah, as I was saying, this increases the bandwidth. So does the bandwidth. The most common method for transmitting data modes is to connect an, uh, an audio output from a computer sound card to the microphone input of an SSB transmitter, or commonly what you'll see is you'll see a standalone little unit that's sort of like a sound card that's USB on one side of the computer and is audio that goes to the auxiliary audio connector on the back of your radio. Or the newest rigs have a built-in sound card, just one SSB cable, one USB cable going between the computer and the radio. So here is a table of bandwidth for different modes. To give you some comparison here, CW at 20 words a minute, it occupies about 100 hertz bandwidth, and a voice signal on single sideband occupies about 2800 or 2700 hertz bandwidth. About 300 to 3000 hertz is what you transmit. So PSK31 and FT8 are very narrow. Radio teletype and MFSK16 are broader but still fairly narrow. You see as the data goes up, as the data rate goes up, the bandwidth gets broader. So for instance, if you look at Winmore and Pactor 3 and Pactor 4, which are all relatively high speed, are relatively faster data on HF, the bandwidth is larger also than the data communication at the top, PSK31 and FT8, which are fairly slow. So when you're operating, you have to be careful. You have to be careful, just as with single sideband, that you don't operate too close to the edge of a band, so that part of the bandwidth you're occupying is outside. It goes past the band edge. So what that usually means is, pardon me, what that usually means is for most data modes, you can't get too close to the top edge of the CW segment of a band, and for radio teletype, you can't get too close to the lower edge of a band. And to be polite, you have to watch out and try and stay within the bandwidth of the frequencies that are used by gentleman's agreement for each mode. Let me talk about transmitter duty cycle here. Most ham radio transmitters these days are designed for a single sideband. So single sideband, there are power peaks that correspond to the loudest parts of speech, but most of the time, the transmitter is operating at reduced power, and so. And then for CW, you're keying the transmitter on and off. So CW, when you're transmitting, because of the spaces between dits and das, you're only operating at full power 40 or 50% of the time. Single sideband, because your voice has peaks and lower level parts, lower volume parts. You're transmitting at full power 25% or less of the time. Well, you need to you need to watch out for that. Now, notice here it says FM modes operate at full power the entire time of transmission. That's because the output of an FM transmitter uh, is modulated by changing the frequency and not the amplitude, whereas AM and single sideband and CW, you're changing the amplitude, or in other words, the strength of the signal. So the thing is, because HF transmitters are not usually designed to run at full power all of the time, you have to watch out. You can overheat them, or you can even damage them. What you usually do is reduce the output power to one half or less, so that you aren't generating as much heat in the power amplifier of the transmitter. Now, what I do as a rule of thumb is I operate I operate digital modes at the same power as is recommended for AM. Because if you think about it, when you're transmitting in AM, the carrier is on 100% of the time. So you're operating near full power 100% of the time. So for my particular rig, I think that the you can get away without get 50% or higher, but I usually, instead of, when I operate FT8, instead of operating at 100 watts, I operate at 30 or 35 watts, and I have no problems. So that's something to watch out for when you're on the air. Digital mode signal quality. Digital modes can generate interference, sure, but there are things you can do wrong also. You can generate unwanted signals by overdriving you can overdrive the transmitter, which introduces distortion, or in other words, as I was saying last week, it introduces when I talked about linearity, it introduces frequency components that weren't there in the original signal, and that shows up as interference to signals that are on slightly different frequencies from yours. You can also have too low an audio level going into your rig. So, and it says microphone input here. You can connect to the microphone input, but also uh, most commercial most amateur radio rigs that you can buy also have an auxiliary connection, so that you can send signals from another audio source into your radio without engaging the microphone. Um, But at any rate, you can have too low a level too, which means that your overall signal is weaker. What you want to do is watch out that you're not making spurious emissions, which usually show up in data modes which have 100% duty cycle. It shows up as lines at frequencies outside of where you want to be transmitting. So for instance, if you're overdriving FT8, you may see signals on a waterfall display, or be able to hear audio components that are 50, 100, a few hundred hertz away from where you're trying to be. Um, oh, boy, I don't know where this is coming from, but anyway, your transmitter usually has something called automatic level control, or ALC, and you have to adjust that carefully. What you want to do is you use it to prevent, when you're using voice, you want to use that to prevent your voice peaks from overdriving the power amplifier and causing distortion. So what ALC does is it reduces the microphone gain for a moment. Well, for digital modes, which are constant amplitude more or less, you don't want to do that. Um, you don't want to do that. You want to use a little bit of ALC so that your voice peaks don't introduce distortion. Um, and uh, there are also There are also compression settings on most SSB transceivers where you can uh, where you can reduce the peak to average ratio, which means the peaks are as high, but the average is higher. For digital signals, you don't want either one of those. Um, so when you're running a digital mode, you turn off compression, you turn off voice compression, and you adjust you either turn off the ALC or you adjust the audio level so that the ALC meter, the needle doesn't move or it just barely moves, and that means that ALC is not turning on and potentially causing distortion to your signal. And this is a common error where people will forget that. So for a cleaner signal, ALC should be turned off and compression should be turned off, or ALC should not engage, at least based on the level of your signal. So where are we here? Okay, so let's do some questions. Which mode is normally used when sending radio teletype signals using audio frequency shift keying with an SSB transmitter? USB, DSB, CW, or LSB? Upper double CW or lower sideband?
A.
I thought it
Well,
was
the
lower
answer is,
side.
remember, radio teletype is the exception. It's lower sideband.
Lower, right?
Yeah,
Uh,
everything else is upper.
ah,
I tell you, it's all arbitrary. This is unfortunately stuff where you have to memorize most of it. What is the standard sideband for JT65, JT9, FT4, FT8 signals when using AFSK? Lower sideband, upper sideband, double sideband, or single sideband?
That one's upper, isn't it?
Yeah, the answer is B, upper sideband. So for everything but radio teletype, think upper sideband on a single sideband transmitter. What could be wrong if you can't decode a RTTY or other data signal even though you think it's tuned in properly? A, the market space frequencies may be reversed. B, you may have selected the wrong baud rate. C, you may be listening on the wrong sideband. Or D, all these choices are correct.
Delta.
Yeah, it's delta. That's right. Now, A is very unusual, but because that would imply that the transmitting station is sending the market space frequencies reversed, but it's also an effect of listening on the wrong sideband. If you're listening,
What are you doing? Get out of there.
choices are correct. So you got to be on the right sideband, get the right baud rate, and get the right frequencies tuned in. What should the A Why should the ALC system be inactive when transmitting audio frequency shift keying data signals? A, ALC will invert the modulation. B, the ALC action distorts the signal. C, when using digital modes, too much ALC can cause the transmitter to overheat. Or D, all these choices are correct.
at least go with C.
Maybe D.
Yeah, I'm thinking D, but
Well, I'm sorry, the answer is B. ALC action can
oh,
distort the signal. So you want it either turned off or so it is not engaged or barely engaged. I don't think I can turn the ALC off on my radio, so when I'm using FT8, I set my transmit level to where the ALC meter needle doesn't move, or I can just barely perceive a little motion. Why is it important to know the duty cycle of the mode you're using when transmitting? A, to aid in tuning your transmitter. B, some modes have high duty cycles that could exceed the transmitter's average power rating. C, to allow time for the other station to break in during a transmission. Or D, to prevent overmodulation.
Probably D.
No, the answer is B, bravo. You need to know the duty cycle of the mode you're in so that you don't exceed the average power rating of your transmitter. Remember, I was saying that CW and single sideband are only run at peak power part of the time. Data signals you run at peak power all of the time, and if you do that for too long, you can overheat your final amplifier in the transmitter. What is the relationship between transmitted symbol rate and bandwidth? A, they're not related. B, higher symbol rates require wider bandwidth. C, lower symbol rates require wider bandwidth. Or D, bandwidth is half the symbol rate.
Bravo.
Yep, the answer is bravo. Higher symbol rates require wider bandwidth. What is indicated on a waterfall display by one or more vertical lines on either side of a data mode or RTTY signal? A, long path propagation. B, backscatter propagation. C, insufficient modulation. Or D, overmodulation.
Delta.
Yep, it's delta, overmodulation. Okay. I'm going to go through this very fast. We're already at 10 past the hour, so I'm going to try and wrap up in about 10 minutes here. And thank you for sticking with me. So, for radio teletype and PSK and so forth, what you do is you call CQ with your call sign. In this case, in the example KILP, and you end your transmission with a K, which is the same as when you end a CW transmission. And a response would be you call the other guy's call sign and you say, this is my call sign, and end with K. That's because radio teletype PSK31 are conversational modes. In other words, there's no structure that indicates the beginning or the end of a conversation or connection. Pactor and Vera and packet modes have that structure. So so you can initiate a contact with a specific sequence, and you can end it with a specific disconnect message, like bye or D. And it depends on the protocol, but the idea is when you're having to use computer terminology, where you're having a session where you're communicating with another station, there are more formal ways to begin and end it in packet mode than there are in these conversational data modes. So when you want to connect packet radio to a mailbox station, you send a connect message. And if the signal is received, then the other guys, then you send a training sequence of packets to determine between the two stations basically how fast you're going to go. It says which protocol, but basically how fast you'll be able to go with the minimum of errors. This is the same as phone modems. If you remember phone modems, you'd hear a bunch of different sounds before the speaker turned off, and each different sound was the modem trying a higher speed with a slightly different protocol. And it's the same way with packet radio. If they can operate at multiple speeds using different modulation methods, then they will try for the highest speed that makes sense in terms of minimum errors. And if you connect to a gateway or a mailbox station, these are the only stations that are allowed to operate without a control operator. Now, even a repeater is supposed to have a control operator monitoring at all times. And I think John can tell you that the Hazel Park repeater usually has somebody listening just in case there are shenanigans. But but packet gateway and packet mailbox stations can be unmanned or automatically controlled, and so they're restricted to certain band segments, to very narrow band segments. And there's a table of those, and there's a table of those, and they're a very narrow range of frequencies on HF, and other stations under FCC rules must be operated under local or remote control, but they need a control operator in charge at all times. So this is the sole exception. So uh, um, you can see that automatic stations, automatic response stations are uh, can operate in 5, 10, up to 15 kilohertz segments of different bands. When you get to 6 and 2 meters, you can see that you have quite a lot of bandwidth available. On 10 meters, there's also quite a lot of bandwidth available. But most of these are 10, 15 kilohertz, 5 kilohertz, which means that automatically operated stations you're going to find in only a narrow part of the band, and that means they're easy to that means that they're easy to avoid. And that's what you want to do, because if you're operating a station manually and the other guy is too, if somebody gets on your frequency or you get on their frequency, they'll tell you, hey, frequency's in use. But an automatically controlled station can't do that. It doesn't know how to. Okay, so I want to talk about waterfall displays for a minute. This is a waterfall display, and I'm going to show you a couple of brief videos in just a minute. But the idea of a waterfall display is it shows you in real time what's happening, and the signals drift from the top downward. So the most recent signals are at the top, and the oldest signals, which can be several seconds or even a minute old, or even minutes old, are down at the bottom. The frequency is indicated left to right. So the frequency usually increases as you go to the right. And the signal strength is represented by the brightness or the color or both of the traces that are on the display. So I'm going to show you an FT8 display here. This is what you see on WSJTX. And you'll see that it's a little bit different, but what you're seeing here is you're seeing strong signals. You can see some of these are red, like right in the middle of the display, which indicates that they're fairly strong. The ones that are yellow are weaker, and you can see some that look like ghost impressions. You can only see a little bit of yellow. Those are even weaker. And you can see from the timestamp at the top, the timestamps on the left, that the most recent signals received are at the top, and you can see that the frequency within the audio bandwidth that you're decoding in the software goes from left to right, from lowest to highest. Now, what I'm going to do here is I am going to switch for a moment and show you a few waterfall displays in action, because I can um, I can do this, but all right. See, I'm going to do this, and then I'm going to go back to share. I'm going to share this other thing here. There we go. It's a media player. I'm going to put this on full screen here. Oh, where is it? Can people see this
Yeah.
thing that's a media player that's got a waterfall in it?
Yes.
Mhm.
Yeah.
Okay,
Looks good.
go ahead, Carrie.
Yeah, looks good.
Okay, I'm going to turn this on. This is showing all of 40 meters. You notice that it's 7,000 kilohertz on the left and 7,300 on the right. And as this is operating, you can see that signals are going from the top down. So in the top part of the display, you can see the signals in real time, where the vertical axis is the signal strength, and the horizontal axis is the frequency. You can see that varying in real time. And then on the waterfall, you can sort of see the record of that. Off to the left, you can see CW signals, so you can even see the dits and dahs there. And then you saw some interference there briefly, and you can see that band where the noise level goes up for a couple of seconds. But at any rate, that's really typical for a whole band display. And then single sideband is off toward the right there, and you can see that some of these are fairly broad. What you'll see is a sort of ribbon that's about 3 kilohertz wide that indicates the voice signal. So let me bring up a couple others here real briefly. So I'm going to show you FT8. Now you can see that the bandwidth is only a few kilohertz here. It's only 4 kilohertz wide, and you can see in the top part here, you can see a little bit of noise, and you can see two, now three CW signals poking above the noise. And if you look, you can see the dits and dahs in the waterfall. So, and let me show you what FT8 looks like then. Now, FT8, what you're seeing here between 7074 and 7077 or thereabouts is multiple FT8 signals. And I don't know what this guy is doing way off on the left here, but you see multiple FT8 signals, and you can see the tones changing on each one. Now, in this little segment of spectrum, it's very common to see 10, 20, even 30 signals, and the WSJT software um, can decode uh, all the signals in that bandwidth. And so it can decode even signals that you can't see on the display. Now, if you look at this, you can see these signals all turning on more or less at the same time, and 13 and a half seconds later, all more or less turning off. In fact, you can see that green one there? You can see the tones going back and forth among the 8 different audio frequencies. So let me show you what this looks like on the WSJT waterfall now. This one's a little bit different because it's going much slower. Whoop. It's going much slower, and I just lost my display here. Can you see this where it is? Yeah, can you see this where it is showing the signals occupying a fair amount of bandwidth each? And you can see at the bottom there the different signal strengths at different frequencies. And then you can see at the end of each 15-second window, you can see on the left there that the software is decoding a whole bunch of different stations. So it's decoding 20 or 30 different stations transmitting in that audio bandwidth. That's the same bandwidth as a voice signal. Now this one's going much slower. This is several minutes top to bottom. But for the purpose you want to use it, which is to tune and also where you see the dark or light blue areas, that's where there is nobody transmitting. That's how you hunt for a slot where you can transmit. When you're answering somebody or calling CQ, you want it in the segment you're using, which is going to be either the 0 and 30 segment or the 15 and 45 second segment. You want to find a place in that spectrum where nobody's transmitting. Like, for instance, you can see to the left of 1500 hertz and to the left of 1000 hertz, in segments, there are these nice open spaces. All right, so I'm going to stop this now. Whoop. I have to go back and find this again. There we go, screen. There we go. Let's see if I can stop sharing. Okay, stop sharing. And I'll go back to the slideshow now. But at any rate, I hope that gives you a much better idea of how waterfalls work. Now, for audio bandwidth, you'll see that kind of thing in software running on your computer. For RF bandwidth, you'll see that on spectrum displays on newer radios. Usually they generate that using digital signal processing, and as you can see quite a lot of spectrum. You could see all of 40 meters in one display there. And my radio and John's that he was playing with on the break can do that also. It can display quite a lot. Um, and at a minimum, usually you can display 20 or 30 or 40 kilohertz of spectrum. So these waterfall displays are good not only to tell not only to tell if there's interference and other activity where you are, but also to tell where other stations are if you're looking for them. So, all right, so let me share this again. Here we go. Oh, 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 oh. Here we go. All right. So you should be seeing the one slide again. Now there are other tuning aids that you can have. These are older ones for radio teletype. On the left here, what you'll see is a display on that you can see on FL which is software that you can decode radio teletype. And what you're seeing in the left center, in the center upper here, is the spectrum of a frequency shift keyed signal. You see there are two peaks, and those yellow lines are the frequencies where you should be lining up the signal so that it's centered properly. And below that, you'll see a waterfall, and you can see that the signal is quite noisy because these peaks are kind of spread out and not well defined. And then on the right-hand side, you'll see an older type of display where you'll see the mark and the space frequencies at right angles. And the idea is, and again, this is a noisy signal. So what you should see is, for a strong signal, you'll see fairly narrow lines that are vertical and horizontal. And when you're tuning the signal in, you want to tune it so that they are straight up and down and straight horizontal rather than tilted. And that says that you're tuned to the right frequency. And then because you can see things that aren't part of these vertical and horizontal loops, you can see little dots there. That's an indication of noise. Of noise in the signal. But this is an older method of tuning, excuse me, radio teletype signals. And back in the analog days, you would see this kind of display on an oscilloscope. So there we go. So, and this explanation is more or less what I went over. So the idea is to tune the mark and the space frequencies to right where they should be. So on the left, it's lined up with the yellow lines, and on the right, it's horizontal and vertical on the cross display. Third-party traffic. I think Marv may have said something about passing messages for other people, and in most cases, it's legal to pass messages on behalf of third parties. Certainly between stations in the United States and between stations between us and the U.S. and other countries, if it's not forbidden by international regulation. Well, that applies not only to voice and CW transmission of messages, but also digital mode transmissions. So you have to watch out for that. So third-party messages apply to everybody. The rules apply to, I'm sorry, all modes, regardless of how it's accomplished. You also can't transmit commercial messages. Now, what that means is you can't get on the air and say, for instance, on the Sunday Night Net, uh, I'm operating Wes's antennas now, and I'll give you good prices on stuff that I sell. That's an ad. What you can say is, what you can say is, I'm thinking of selling my old radio, and if it's a so and so, and if you're interested, why not call me up or ping me on email? Uh, so, if you have junk in your shack that you want to sell, that's okay. But if you're making it a business, FCC says no. That prohibition of commercial messages goes way back to the early days of radio, when there was not much difference between amateur and commercial stations. And the prohibition on commercial messages is why we're called amateur radio. Interfering signals. You have to watch out. One thing is, and we'll talk about propagation in a few weeks, but uh, on some bands, you often cannot hear both ends of a conversation. So you may think that a frequency is clear when somebody distant is transmitting, but you can't hear it, but you can hear the guy he's talking to when it's the other guy's turn. So, um, so so that means that one station in a cell might be hidden from you, but that also means that you're probably hidden from one station that's already in the Q cell. And you have to watch out. It's unintentional, but you have to watch out for that stuff. And this is just the same as on voice. If you have to watch out, I'm sorry, if you're causing interference, then it's up to you to be polite and apologize and go somewhere to a different frequency. So uh, packet modes are a little bit different because you can't break into a packet mode, but you can ruin the connection. You can interfere with the connection between other stations. And it's a thing where you have to be more careful, because it's not as if one of the other stations can tell you, hey, the frequency's in use. It's something that you have to do. So let's do some practice questions here. And I think we're near the end. And thank you very much for sticking with me. What's required to conduct communications with a digital station operating under automatic control outside the automatic control bands segments? A, the station initiating the contact must be under local or remote control. B, the interrogating transmission must be made by another automatically controlled station. C, no third-party traffic may be transmitted. D, the operator of the interrogating station must hold an extra class license. Um, any guesses?
Either A or B.
I said A.
Yeah, it's A actually. And this is a little bit of a trick question, because the automatic station has to be within one of those narrow band segments where they're allowed. But you might be on a different frequency and it can hear you. That's the only way this question works. But yeah, automatic to automatic you can't do. Uh, the station that talks to an automatic station, the other guy has to be under positive human control, one way or another. Under what circumstances are messages that are sent via digital modes exempt from Part 97 third-party rules that apply to other modes? A, never. B, when messages are encrypted. C, when they're not encrypted. Or D, when they're under automatic control.
Must be D. We didn't talk about encryption.
Wait a minute.
No, the answer is A.
Yeah.
Third-party rules for passing messages for third parties apply regardless of what mode you're using. So the answer is A. You
Yeah.
can't you can't exempt messages from the third-party rules just because you're using a digital mode. Now again, this is a relatively uncommon occurrence, because there are third-party agreements with most other countries and the US, but you might occasionally run into it. And certainly US to US, the rules say that it's okay. Yep, sorry, yeah, the answer is A. On what bands may automatically controlled stations transmitting Radio teletype or other data modes communicate with other automatically controlled digital stations. A, on any band segment where digital operation is permitted. B, anywhere in the non-phone segments of 10 meters or shorter wavelength bands. C, only in the non-phone extra class segments of the bands, or D, anywhere in the 6 meter or shorter wavelength bands and in limited segments of some of the HF bands.
A.
No, the answer is D. And
Okay.
again, this is a little bit of a tricky question because when
Yeah.
you're operating on HF, you can only talk to an automatic station when the automatic station is in, I'm sorry, the automatic station can only talk to you in on limited segments of the HF bands. On VHF and up, that limitation isn't there, but uh, on HF, yeah, you're limited to these narrow the automatic stations rather can only transmit in these narrow 5, 10, 15 kilohertz segments. What symptoms may result from other stations interfering with a backdoor or VARA transmission, in other words, packet radio? A, frequent retries or timeouts. B, long pauses in message transmission. C, failure to establish a connection between stations. Or D, all of the above.
D.
D, that's correct.
D.
All of the above. All these choices are correct. The following way to establish contact with a digital method: the control operator. B, send QRL in Morse code. C, respond when the station broadcasts SSID. Or D, transmit a connect message on the station's published frequency.
Probably D.
Yeah, the answer is D, because a gateway station is automated. The only way you can do it is to follow the proper protocol that it's listening for, which includes the right frequency that it's listening on and the right kind of message to start a session. The SSID is actually, that's a Wi-Fi term. What action results from a failure to exchange information due to excessive transmission attempts when using ARQ mode and ARQ mode? A, the checksum overflows. B, the connection is dropped. C, packets will be routed incorrectly. D, the encoding reverts to the default character set.
B.
Sorry?
Bravo.
Yeah, the answer is B. If you have too many retries, too many transmission attempts, the connection eventually fails and it gets dropped. Which of the following describes a waterfall display? Oh my, that's a lot to read. Frequency is horizontal, signal strength vertical, time is intensity. B, frequency is vertical, signal strength is intensity, time is horizontal. C, frequency is horizontal, signal strength is intensity, time is vertical. Or D, frequency is vertical, signal strength is horizontal, and time is intensity. Another trick question. Anyone want to guess? Do you remember what the displays were?
Frequency is horizontal.
Yep. So far, so good.
That's
What
A
did
or C.
what did the falling part of the display indicate? What did it mean when something was falling on the display?
It was getting
Uh,
old. It's the old stuff.
Okay, so what answer then?
A.
It must be C.
Okay, the answer is C, and this is another kind of tricky question. Frequency is horizontal. Remember, it was horizontal across the top of the display. that I was showing, and time is vertical. The record of the signal gets older as it falls down the display. So signal strength is the intensity. Remember I said the intensity or the color, depending. So on
Yeah,
some of the displays, the signal got brighter. I'm sorry, as the
it's horizontal.
signal strength was stronger, the display got brighter, and on some of it, on the WSJT display,
Time is
it changed colors depending on the signal strength. But at any rate, frequency horizontal, time vertical is the answer you want. And just try to remember that video you saw, or just look at any waterfall video on YouTube, and it'll show you the same thing unless it's an actual waterfall,
frequency
water
horizontal.
falling over a cliff.
Signal intensity. Time
Yeah.
vertical. Hmm.
So that's it. So I want to thank you for sticking up this very long time. We have a big we have a big problem with running too slowly, and we may have to do something, either skip the review in a few weeks or do an extra session so that we can catch up. And I apologize on behalf of all three of us. So next week, John is finally going to get into electrical units, decibels, Ohm's law. You have a week now to find that calculator. Make sure it can do logarithms and powers of 10, and maybe square roots would be helpful too.
Chapter 4 next week.
Before next week, yeah. And you
Okay.
can use the calculator on your phone, but if you want to take one to if you want to take one to the
Exam.
exam, you have to have a kind of dumb scientific calculator that's standalone and no graphing and no programming. So,
Yeah.
and I encourage you both to, and all the people who might happen to listen to the recording here, to try the practice test. You're far enough along now that you can be answering questions in different subject areas pretty well. And not only will it make you more familiar, it will make you more confident too, and point out things where you have to go back and read the book some more. And I'm sorry, but you're going to have to do the work to get the license.
Uh, I'll probably use the computer calculator just so you can see what we're doing because they're all different. The keys
Yeah.
is different, so we'll have an example there.
Okay. So until next Monday, that's it.